Hi there, and welcome to Wyzant's online Ask an Expert feature. So in this particular short video, we're going to be taking a look at this Calculus 1 question, which asks us to compute the volume of a three-dimensional object whose base is given by the region bounded by these two curves that you see here. One is going to be this parabola, and the other is going to be the x-axis, or y equals 0. And we're told that this three-dimensional object, when you take cross-sections of this three-dimensional object parallel to the x-axis, what you should see are triangles that have an equal base and equal height. So naturally, the hard part with this question is actually visualizing what this three-dimensional object is going to look like. Once we have a good idea of what that object looks like, the volume is going to come in terms of some simple integral that's very easy to evaluate. So the calculus step is easy. The hard part is actually visualizing what this object looks like. So what I've gone ahead and done here, as you can see here, is I've already thrown down a pair of x and y axes, and I've put them on a slant just to make the visualization into the third dimension a little bit easier to see. And so the first thing we're going to get is the region that this three-dimensional object is going to be defined over. And that's going to be given in terms of these two curves. One is the parabola and one is the x-axis. Now I'm going to go ahead and skip the steps for how you would plot this parabola. I'm assuming that you're comfortable with it. This parabola is going to have a y-intercept of 6 and x-intercept of plus and minus 3. So roughly the region that we're talking about is this parabolic region that's bounded on the top by this parabola and on the bottom by the x-axis. And now here's where we move things up into the third dimension. To understand what's happening in the third dimension, we use our next bit of information, which tells us if we were to take this third dimensional object and cut it parallel to the x-axis, so if we were to slice this object parallel to this direction, parallel to the x-axis, what we should see is a triangle, which I'll put here in red, and this triangle is going to have some base b, and it's going to have some height h. And the important takeaway from this is that the base and the height are going to be equal to each other per the question that we're being asked here. So the way to wrap your mind about what this three-dimensional region is going to look like is it's a region that's defined over parabolic space and has these triangular cross-sections that are created such that the height and base of these triangles are equal to each other. Now that we have this picture in our minds of what this region looks like, now we can start to set up an integral that represents the volume of this three-dimensional object. And the way that we're going to set up this integral is by using a technique called volumes by slicing. And the idea is we're going to consider a very small slice of this three-dimensional object, and we're going to ask ourselves, how would I compute the volume of this tiny slice? And so that's what I'm going to do on the next slide, on the next board here. So imagine we have a small slice of our region here that would look something like the following. What would be the volume of this small slice? Well, the volume would be the thickness of this slice, which approximately is going to be given by dy, a very small change in y. And that's given from the fact that in this diagram here, you can see that we're varying the y variable just a little bit to get a thickness for this small volume. And then we have to ask ourselves, okay, what about the area of this triangle? What's the area of this triangular region that's right here? Well, we're given that the base here is going to be b and the height here is going to be h. So that area would work out to be 1/2 base times height. So in total, the very tiny volume for this thinly sliced region of our total volume is going to be equal to the area of this triangle, which is 1/2 base times height, and then times this small thickness value, dy. And so now hopefully you can start to see that we're getting close to setting up an integral here, but one of the things that we need to know is how does the base and the height vary with the y variable? Once we know that, then we've basically got an integral that we're ready to solve. And so here's one of the critical observations. First, we use the fact that the base and height are equal to each other. So that allows us to write an expression solely in terms of, for example, the base. So we'll write this as 1/2 base squared dy. Another thing that we can do is we can go back to our picture, our diagram of this parabolic region, and take a look at how the base relates to the x coordinate of a point that's on this parabola. And if you stare at this particular diagram long enough, hopefully you can see that in fact the base is going to be equal to 2 times the x coordinate of a point that's on this parabolic region. So what I'm going to do next is I'm going to make the replacement that this b that's in here is actually equal to 2 times x. Now we're not done yet setting up the integral that we want to evaluate. We still have x here, and what we really want is for x to be written in terms of y. How do we do that? Well, this is again where we recognize that this x value that's coming right here, this little x value, has a relationship with y. In particular, x and y are related by this parabola, because this is a point on the parabola. And so what I can do is I can solve the equation of this parabola for x in terms of y. And I'll let you work out that step on your own. And what you'll discover is that this x variable right here is actually equal to the square root of 9 minus 3/2 times y. So that's coming from the equation for the parabola. That's defining our region. And so lastly, we're basically at the final stage here before we're ready to evaluate the integral. So now we have that our small volume, dv, is going to be equal to 1/2 of 2 times, and now instead of an x here, I'm going to put my formula for x in terms of y. So this will be square root of 9 minus 3/2 y. So I have a 3/2 y here, and then this whole quantity is going to be squared, and we're going to tack on our dy for the thickness of this region. And so now, basically at this point, we have an integral. We're going to integrate over all of these small little volumes. We're going to integrate this expression, which is now solely written in terms of the y variable, square root of 9 minus 3/2 y here, all squared dy. So we have this integral expression now in the y variable. And the last question that we have to ask ourselves is, what are the correct bounds for the integration? And this is, again, where we go back to our original diagram for this region, and we see that the y variable starts at the x-axis where y is equal to 0 and goes all the way up to the vertex of this parabola, which occurs at y is equal to 6. And so the correct bounds for this integral are going to go from y is equal to 0 to y is equal to 6. And so at this point, I'll let you go off and calculate this integral. Notice that some very nice things are going to happen involving a square root being squared. So actually, this expression right here is just going to be a simple polynomial in y that's very easy to integrate. And when I went ahead and did this integral, I got the value of 54. And so 54 here is going to represent the volume of this region that is bounded between this parabola and the x-axis, and whose height is sort of given by these triangles that have equal base and equal height. So the final answer to this question is that the volume is equal to 54. And that concludes this video. Thank you so much.